right back to the problem. Okay, sorry for that slight interruption. So we have dispersion forces in the molecule. So we'll write down dispersion forces as well. Now, if we draw a more condensed structure of ethanol, we draw the C2H5OH like this. Well, what do you know about this oxygen when it's got 2 bonds and 2 lone pairs? Just like in water that forms a bent geometry like that, this molecule is going to do the same thing, right? You're going to have the oxygen with the 2 lone pairs. You're going to have a hydrogen down here, and then you're going to have the C2H5 or the ethyl group here. So that means we've got a dipole going this way and a dipole going that way, which produces this resultant dipole. And so we also have dipole-dipole forces. So what's the take-home message? We have dipole forces, we have dispersion forces, and we have hydrogen bonding. So we have literally all 3, dispersion, dipole, and hydrogen bonding, which is D. That is the one that has all of them in there. So a molecule of ethanol, hydrogen bonding, dipole-dipole forces, and it also has London forces, or what we call dispersion forces some of the time. All right, question number 27 asks us, which compound exhibits dipole-dipole forces? So I'll write it down like this. This is my shortened version, dipole-dipole forces, and then I'll just put a question mark, and I'll write down all the molecules. We've got boron trichloride. Put in all those lone pairs because friends don't let friends leave lone pairs out. Then I've got this xenon difluoride. Finish that one up. So this is number 1. This is number 2. What do we got for number 3? We have nitrogen trifluoride. So we got nitrogen. You guys can probably solve this problem faster than me. There we go. And last we have oxygen dichloride. Okay. So we've got some really nice covalent compounds here. Number 3 and number 4. So this is why we spent so much time in general chemistry looking at molecular geometries, didn't we? Well, if we look at the first one, boron trichloride, you should know that that boron is going to be the central atom, of course, and that the chlorines are all going to get away from each other as far as possible. All those bond angles will be 120 degrees. Are there polar bonds in the molecule? Yes, but the dipoles cancel. So there's no dipole in this molecule. Okay? This molecule is trigonal. Come on. Trigonal planar. If we look at the next one, we have the xenon difluoride. Well, I'm not going to redraw the molecule. I'll just show you that these 2 bonds between the xenon and fluorine, they want to get as far away from each other as possible, right? So this adopts a bond angle of 180 degrees. This is a linear molecule, right? Linear. So if it's linear, sure, I have a dipole going this way and I have another dipole going that way, right? Fluorine is the most electronegative element in the periodic table. However, the dipoles cancel. So we'll put here dipoles cancel. So it's non-polar, the same way boron trichloride was. So let's take a look at the next one, which is nitrogen trifluoride. Now, if we redraw nitrogen trifluoride, we have those 4 regions of electron density. We got a lone pair and 3 fluorines. So one of the fluorines we're going to draw on the back, another one we'll put out in the front, and the other one in the plane of the screen, like that. So are there polar bonds in this molecule? Heck yeah. All right, I have a strong dipole going this way, another one going this way, and another one going this way. So if I have all 3 of those dipoles pulling downward to the 3 points of a triangle, overall the resultant dipole is going to be pulling down in this direction, right? Because all the bond angles are 120 degrees. And so this is a polar molecule that's going to experience dipole-dipole forces. Likewise, with the OCl2, I have my oxygen with my 2 lone pairs. I'll draw those in the plane of the screen. I've got a chlorine going behind the page or the screen like that, and I've got another chlorine coming out like this. Now, there are other ways you can draw the molecule, but the point still stands that I have a dipole this way and a dipole this way, right? Oxygen is the second most electronegative element in the periodic table. So I have a dipole going in this direction. If you want to show the dipole towards the lone pair, go ahead, but you can just leave that out. Oops. And you can clearly see that we have a polar molecule, so polar. And so the answer is number 3 and number 4. So 3 and 4, which is answer C. Question 28 deals with boiling point. So it asks you which substance has the lowest boiling point. So which one takes the least amount of energy to convert the compound from the liquid phase to the gaseous phase. So we have number 28. So we want lowest boiling point. Okay. Remember what a boiling point is. It's the temperature at which the vapor pressure is equal to atmospheric pressure. So we want to convert the liquid to a gas. 1A, I'll just draw a bond line structure here since we covered those in organic chemistry. I have this molecule. This is called trimethylamine. Okay, it tells you the molar mass is 59 grams per mole. Then we have what's called triethylamine. Again, I'll draw the bond line structure because we covered those in the organic chemistry section. It's pretty similar to trimethylamine, isn't it? Except the molar mass is significantly more. It's 101 grams per mole. Then I have this molecule. This is called ethylamine. Again, you don't have to know the names of these molecules, but you have this CH3, CH2, and then another CH3, and then you've got a NH2 over here, and that's number 3. And then for number, or for D, sorry, there's not a number here, is there? I am losing it. There we go. And then for D, we have the 2 methylenes. We have an NH2 over here, and we have an NH2 over here. Now, the question is asking us about the lowest boiling point, right? The ACS type exams love to ask questions in this way. I always think about things in terms of what's got the highest boiling point. Now it's asking us the opposite. Which one's going to have the lowest boiling point, right? Which one takes the least amount of energy to convert it from a liquid to a gas? Well, I have a question for you first. Could you tell me which one of these compounds, A, B, C, or D, has the highest boiling point? Let's flip it on its end, and then we'll see if we can solve the problem. Which one has the highest boiling point of all? Okay, we get some interesting answers here. Okay, well, if we think about the type of intermolecular force that these, that these compounds can experience, right? A and B both have dipoles in them, don't they? Right? Because the carbon-nitrogen bond is polar. So these molecules can experience dipole-dipole forces. Dipole-dipole forces. And dispersion forces, of course, but dispersion forces are weaker, so I'll not worry about those yet. But what can these 2 molecules experience, right? Both of these can participate in hydrogen bonding, which is the strongest type of intermolecular force, right? This one has an NH2, right? So it's got 2 nitrogen-hydrogen bonds, and this one has 2 NH2s. So this one will have the highest boiling point, right? Because it's got the most opportunity for hydrogen bonding. This one has the second most opportunity for hydrogen bonding, and so it's going to have the second highest boiling point. So then it boils down to A and B. Which one of these has the lower boiling point? Well, they're both very similar, right? They both have dispersion forces. They both have dipole-dipole forces. But now we're going to base it off of molar mass, right? This one's lighter. It has less electrons, therefore less dispersion forces. And so A is going to take the least amount of energy to convert from a liquid to a gas. And so the answer is A is going to have the lowest of all the boiling points. Well, let's talk about freezing point for a second. And again, this goes right back to your general chemistry 1 days. Okay, this is question 29, and we're looking for lowest freezing point. Lowest freezing point. Okay, and what do we have? We've got a 1.0 molal solution of potassium sulfide. We've got a 1.0 molal solution of ammonium chloride. We've got a 1.0 molal solution of glucose, C6H12O6. And then D says all are the same. All are the same. Well, that's probably not true. But anyhow, this goes back to colligative properties. Okay, this question is about colligative properties. If you have ever lived in a northern climate, maybe you lived on the East Coast, like I grew up in East Coast of Canada, and what did they put on the roads in the winter? Right, they put salt, sodium chloride on the roads. Why did they put salt on the roads? Well, the salt, what it does is it lowers the freezing point of water, right? When I add sodium chloride crystals or sodium chloride to the water, it lowers its freezing point. Water normally freezes at 0 degrees Celsius. But if you have a really cold day, you don't want all the water to freeze on the road and make everything icy. So when they add sodium chloride to it, then let's say the freezing point becomes minus 20. So if it's minus 15, that means that all the ice will be melted, and then you have no slippery ice to worry about. Well, what is it about the sodium chloride that lowered the freezing point? Right, you should know about a boiling point elevation and freezing point depression or lowering. Okay, and that's depression. And that's what this question is about. The reason why sodium chloride causes the water to freeze at a lower temperature is because it disrupts the formation of the crystal lattice, right? Those particles. So it's based off of the number of particles, which is found in the Van 't Hoff factor. So we say the change in the freezing point is equal to I, the Van 't Hoff factor, multiplied by M, the molality, multiplied by Kf, the molal freezing point depression constant, right? The Van 't Hoff factor is nothing more than the number of particles. So if I look at these three compounds, they all have the same concentration, right? And I'm talking about a solution of each one of these in water, right? I can imply that these are all aqueous solutions. So the question then becomes, which one of these is going to produce the most particles? Well, the potassium sulfide is going to break into 2 potassium ions plus a sulfide. The ammonium chloride is going to break apart into an ammonium ion plus a chloride ion. And the glucose is just a molecular compound. It's not ionic. So you're only going to end up with 1 particle. Here we have 3 for our Van 't Hoff factor. Here we have 2 for our Van 't Hoff factor. And here we have 1 for our Van 't Hoff factor. So which one is going to affect the change in freezing point the most? It's going to be the one that has the most particles, the potassium sulfide. There we go. So what would you have to review in this case? Colligative properties, freezing point depression, and boiling point elevation. All right, let's take a look at question number 30. It says, which arrow on the phase diagram best corresponds to a substance being heated? Let me go right back to the exam here, and we'll see. A picture's worth 1,000 words, isn't it? So where is it? It's right here. It's this question here, number 30. Which arrow on the phase diagram best corresponds to a substance being heated between C and D, or being heated between C and D on the heating curve? Okay, so this area. Well, let's label the heating curve, right? And then we have, this is a phase diagram over here, and this is a heating curve. So what's happening on the heating curve? Right, here we have a solid, okay? And the solid is being warmed up over a certain amount of time. The temperature of the solid is increasing. Think about it. And if you're like, well, how could you increase the temperature of ice? Well, you can definitely increase the temperature of ice. If you have ice that's at, say, minus 50 degrees Celsius, let's say minus 50 degrees Celsius, what is it? It's frozen. If you have ice at minus 5 degrees Celsius, it's still frozen, but it's warmer. Right, so you can warm up ice, right, without melting it, okay? So this is heating up a solid, okay? Now what's happening here? This is the phase change. This is the process of melting, right? All of the heat that's being absorbed, because you're like, why isn't the temperature changing? Because all of the heat that's being absorbed, none of it is causing an increase in temperature. It's all going towards the melting of the substance, right? Okay, so what's happening here is that now I have my liquid, okay, and what am I doing? I'm warming the liquid. Liquid being warmed. Son of a gun. Get me back into a classroom. Liquid being warmed. Like that. Then here we have boiling. Then here we have vapor being heated or warmed, whatever you want to call it. Maybe I should have said heated instead of warmed, but you get the idea. Oh, right. There we go. So now let's look at the phase diagram. Well, you should know that on the far left-hand side of the phase diagram, this is a solid, low pressure and low temperature. Then as I increase the pressure and temperature, I have the liquid phase in here, and I have the gas phase over here. This is the triple point right there. So which one of these represents a liquid being warmed? All right, it's going to be number 2. You see that it remains a liquid the entire time on this arrow, okay? And it's going from a lower temperature to a higher temperature. So that represents a liquid getting hotter or being warmed, or increasing its thermal energy. All right, so the answer is 2. Good question where a picture is worth 1,000 words. Give me a thumbs up if you follow me on that one, or stop me if you have a question. Again, stop me at any point if you have a question. This is the land of the free for 2-3 more weeks. All right, good. Thanks, Brogan. Thumbs up. Right on. Maybe I should get a t-shirt made for the fall that just says thumbs up with a question mark. Maybe an apron. That would be cooler. Maybe a lab coat. Nah, that's uncool. Okay, where are we? Question number 31. Deals with the kinetic molecular theory of gases. It says, according to the kinetic molecular theory, why does the pressure increase as the temperature of an ideal gas increases? So this goes back to the kinetic molecular theory of gases, General Chemistry 1. So let's see, we got the gas molecules collide more frequently with the wall. Well, yeah, right? If you heat up the gas, the molecules are going to be moving faster. Therefore, they're going to hit the wall more frequently, right, if they're moving around faster. And then do they have more energy? Well, yeah, if we have the temperature increasing and they're moving faster, then they're going to have more thermal energy, and therefore they're going to collide just with more energy against the wall. So both of these are true, number 1 and number 2. Kinetic molecular theory of gases. Let's take a look at question 32. There are a few ways you could solve this problem. Which gas is most dense at 2 atmospheres and 400 Kelvin? Okay, you can use the formula that density is equal to pressure times molar mass divided by RT. This is a formula I know. I remember teaching it to my students. D is equal to the pressure times the molar mass divided by R divided by T. So if R is a constant, T is a constant, if the pressure is constant for all of these, that tells you that density is directly proportional to molar mass. So then you just have to look at the molar mass of all 3 of these gases. And when you look at F2, N2, Ne, and O2, well, neon only has a mass of 20 and fluorine is 19. You got 2 of them, so that makes 38. So it's going to be fluorine. Right now, if you don't remember how to derive this formula, the density is equal to pressure times molar mass divided by RT. I went over a derivation of that in General Chemistry 1, where you have density is equal to mass over volume, right? And then you solve for number of moles as being equal to mass or molar mass. Mass divided by molar mass is the way I should have put it like that, because you have mass in grams. And then you have molar mass. Why the hell is there a ruler? In grams per mole, right? So that gives you moles. So then if you have PV is equal to nRT, you can rewrite it as P times V is equal to M, little m, mass over molar mass times RT. Then you can solve for M over V. And you get the M over V, which is equal to density, is equal to P times M divided by RT, like that. So that's how you derive that formula. But again, density is directly proportional to molar mass. All right, question 33. I think I'm going to need a blank page a Taylor Swift blank space to solve this problem. It says, what's the percent yield when you have 1.72 grams of hydrogen peroxide? It decomposes to give you 375 milliliters of oxygen at 42 degrees Celsius, CHA, in 1.52 atmospheres. And they've given us a beautiful, gorgeous balanced equation. And they've given us the molar mass of hydrogen peroxide. Well, oxygen is a gas, and we've been given the volume, the temperature, and the pressure, so we can figure out the number of moles, can't we? Right? Yeah, absolutely we can. All right, so let's take a look at this one. And again, I'm going to need some room here. Give me some room. All right, where were we? So this is question number 33. Hopefully there's enough room to solve it here. So we have 2 moles of hydrogen peroxide produce 2 moles of water plus 1 mole of oxygen. We're starting out with 1.72 grams of hydrogen peroxide, and they tell us that the oxygen that we collect, we have a volume of 0.375 liters. It's at a temperature of 42 degrees Celsius, which I've gone ahead and calculated as being 315 Kelvin. And then we have a pressure, so this is our volume, this is our temperature, this is our pressure, 1.52 atmospheres. And we're asked to determine the percent yield. That's the whole point of the problem. What is the percent yield? Why don't we figure out the theoretical yield first? Because if I start out with 1.72 grams of hydrogen peroxide in all of the water in the universe, or sorry, I don't even have to think about it. This isn't a limiting reaction problem. But if I have 1.72 grams of hydrogen peroxide, okay, let's figure out how many moles of oxygen I could make. So I have 1.72 grams of hydrogen peroxide. I know that in 1 mole of hydrogen peroxide, I have 34.02 grams of hydrogen peroxide. If I was to stop right here, all I would have is the number of moles of hydrogen peroxide. Okay, but I need to determine the number of moles of oxygen that I could make. So I need another conversion factor. I know that for every 2 moles of hydrogen peroxide that are consumed, I form 1 mole of oxygen. So I have 2 moles of H2O2, and I produce 1 mole of O2, like that. Units cancel. I end up with the number of moles of oxygen that I could produce, right? The maximum. So let's see here. This is 0.0253 moles of O2. And remember, this is a theoretical yield. Theoretical yield. This is best case scenario, but it's not reality, is it? Now what we're going to do is we're going to use our volume, temperature, and pressure, and we're going to use PV is equal to nRT, and we're going to solve for N. N is equal to PV divided by RT. We have our pressure, 1.52 atmospheres. We have our volume, 0.375 liters. We have our gas constant, which is 0.08206 liters times atmospheres divided by moles times Kelvin. We have our temperature, 315 Kelvin. Looky, looky. Kelvin cancels, liters cancel, atmospheres cancel. We're left over with moles. And the actual number of moles of oxygen that we produced was 0.0221 moles. So now to calculate the percent yield is equal to the actual yield divided by the theoretical yield multiplied by 100%. I end up with 0.0221 moles divided by 0.0253 moles. Moles cancel. I multiply all that spinach by 100%, and I end up with 87.4%. That better be one of the answers. It's D, 87.2, so close enough for jazz, okay? So the answer is D. So a little problem here of just using what? Ideal gas law to determine the number of moles of a substance, using a little bit of stoichiometry to figure out the theoretical yield, and then knowing the formula for calculating percent yield. All right, let's take a look at a problem that deals with reaction rates. So this is question number 34. I may have to go back to my exam here. So question number 34. There we go. It says, what is the correct statement regarding the reaction 2A plus B produces 2C. And we have all these different scenarios. The rate of consumption of A is half the rate of the consumption of B. The rate of consumption of B is double the rate of formation, so on and so forth. Well, if we write out the relative rates of each one of these, we would say that the rate of 1/2, the rate of the disappearance of A, or the change in concentration of A over time, is equal to the rate of the disappearance or the change in concentration of B over time, which is equal to half of the change in the concentration of C over time. Now, I know it's a little unclear maybe, or it's hard to see, but anyhow, so if we take a look at A, okay, it says the rate of consumption of A is half the rate of the consumption of B. Well, if we rearrange this part for the rate of consumption of A, we have the delta, or the change in the concentration of A, the rate of its consumption, is going to be equal to 2 times the rate of consumption of B, like this, so -2 like that. So that's twice the amount, so twice, not half. So this is not the answer. If we look at B, we're going to go through each one of these. We look at B. It says the rate of consumption of B is double the rate of formation of C. So if we write out the rate of consumption of B, okay, over time, it is equal to 1/2 times the change in concentration of C over time. So it is not double, okay? It is half. So this one is incorrect. If we look at C, it says the rate of consumption of B is half the rate of the consumption of A. Well, that one makes the most sense to me, because if you just write out the relationship, you have -1/2 times the change in concentration of A over time is equal to negative of the change in concentration of B over time. So yes, the rate of consumption of A is half the rate, the rate of consumption of B is half that of A. And so this one is correct. And then I'm kind of running out of space here, but it says the rate of formation of C is equal to the rate of consumption of B. You can clearly see that that's not true, because I have a factor of 1/2 in front of my change in concentration of C over time. And so this one is not true. No, and so the answer is C, like that. A little bit on reaction rate. So now we're into the general chemistry 2 questions, I guess. It's kind of where we're moving on to here. All right, let's take a look at 35. I'll try to squeeze the answer in here, since I don't want to copy down this table. It says, what is the reaction order with respect to reactant G? So we're just thinking about G. So let's compare the first 2 reactions, right? Because the concentration of J remains constant, right? Our reaction rate is going to be equal to the rate constant multiplied by the concentration of G to the power of X times J to the power of Y. But if I compare reactions, I'll call this one 1 and I'll call this one 2. Okay? If the concentration of J doesn't change in either of them, I can just leave that out. So if I take the rate of 2 and I divide it by the rate of 1, I get 8.8 divided by 2.2. I'm just going to cross all this out because it's identical. It's going to be equal to 0.2 to the power of X divided by 0.1 to the power of X, like that. You take 88 divided by 22, you get 4 is equal to 2 to the power of X. X is equal to 2, and so the reaction is second order with respect to G. All right, number 36. Based on the information below, what is the rate law for this reaction? We have the overall reaction, and then they've provided the steps of the mechanism here, right? So we see A is in here, which is an intermediate, right? Because it's included in the steps, but you don't see it in the overall reaction anyhow. That's neither here nor there. Now, you would remember that when we covered these types of rate laws, that when the first step is the rate determining step, that step should predict what the rate law is going to be. And so since the rate is simply, or since the reaction is simply A2 produces 2A, the rate is going to be equal to, rate is equal to K times the concentration of this A2 only, right? First step is the rate determining step. So there we go. Number 37. Which statement is true regarding the energy profile provided? The reaction is exothermic. Well, if we look at where we start and where we end, okay, if you were to take a ruler, take the ruler and put it here like this, you can see that our final product is higher in energy than our starting material. And so this is an endothermic reaction. Endothermic. So not true. Now, if we take a look at the two steps, right? We have a transition state here and we have another transition state here. Well, the activation energy for this to this first transition state, so we'll call this activation energy 1, and then we could call this, we'll call this activation energy 2. Well, activation energy 1 is much bigger than activation energy 2. And so step 1 is going to be the rate determining step. Rate determining step. So B would be the right answer, right? Step 2 is not going to be the rate determining step. The reaction goes through two stable intermediates. Well, no, a transition state is not stable. You remember the description in the book, and then I explained it to you. The transition state is like if somebody took a picture of you floating in the air. Well, you can look at the picture, right? But it's not something that was stable, right? It was short-lived. All right, there we go. So rate determining step is the one with the highest activation energy. Question 38 deals with a little bit of acid base, right? Which substance is acting as a Lewis acid? So you should remember that a Lewis acid is an electron acceptor. So if I look at this, if I look at the Lewis structures here, I have the boron trifluoride, and I'll just write out the Lewis structure here. You have BF3, right? The boron is sp2 hybridized. It's got the empty p orbital. And then when it sees that fluoride, the fluoride is going to donate electron density in here. So who's accepting the electrons? The boron in the BF3. So boron trifluoride is the Lewis acid. The tetrafluoroborate, the BF4 minus, that's just the product. That is not a Lewis acid or a Lewis base, right? If you're at BF4 and then the formal charge is on the boron, like so. Okay, number 39. When the reaction is balanced, when this reaction is balanced in acidic solution, the final equation has blank protons on the blank side of the reaction. Well, this one is redox. So balancing redox. Okay, redox reaction, and we have to balance it. So I'm going to definitely need some room to do this. We spent a good chunk of a day doing that this semester. We looked at a pile of redox reactions that we wanted to balance in acid or in base. So this is question number 1, number 39. Here's our reaction. Let me find it here on my screen. This is called the dichromate, Cr2O72- plus zinc, and then we produce zinc ions plus chromium 3+. Okay, now what were the steps that we wanted to take to balance a redox reaction? We have to balance the elements, that aren't hydrogen and aren't oxygen, step 1. Then we're going to balance oxygen with water molecules. Then we're going to balance hydrogen with protons. And then we're going to balance charge with electrons. Now, are there steps beyond that? Yes. You have to make sure the number of electrons cancel. So, and then cancel electrons when adding the two reactions together. Okay, so that's the last step. All right, so, and also there's a first step, which is separate the half reactions. So separate half reactions. All right, here we go. So let's do the oxidation first. So if we have the zinc producing zinc 2+, I'm going to leave out the states of matter. The elements are balanced. There's no oxygen to balance. There's no hydrogen to balance. We have to balance the charge. We have a charge of 0 over here. We have a charge of +2. So we need 2 electrons. +2 plus -2 gives you 0. There you go. Now the first part is done. Remember, this is the oxidation half reaction. Now we're going to balance the reduction half reaction. We've got the dichromate ion. I'm going to need more room. Let's do it down here. We've got the dichromate ion, Cr2O7, 2-, producing Cr3+. So in the first step, we're going to balance the elements that aren't oxygen or hydrogen. So we have 1 chromium in the reactants, and two chromiums in the reactants, and we only have 1 chromium in the product, so we need to have a 2 here. Now we're going to balance out the oxygens. I have 7 oxygens here, and I have 0 on the other side. So I'm going to need 7 water molecules. Now I have a total of 14 hydrogens over here. So I'm going to have to add 14 H+ on this side. What's next? I need to balance out the overall charge. Here I have 2 times 3+, so that gives me +6 on this side. Here I have 14+ and 2-, so that gives me +12 on this side. So that means I need to add 6 electrons over here to balance out the overall charge. Now, I've got 6 electrons in my reduction reaction, and I've got 2 electrons on my oxidation reaction. So I'm going to take that entire oxidation reaction, I'll multiply the whole thing by 3, and I'll end up with 3 zincs produce 3 zinc 2+ plus 6 electrons. Now I can take this half reaction and I can tally it up with this one, and I'll end up with my overall redox reaction. So the electrons cancel, and I end up with 3 zincs plus the dichromate ion plus 14H+, and you can see what the answer is already, produces 3 zinc cations plus 2 chromium cations plus 7 water molecules. And so the question was, how many hydrogens? The answer is 14 of them, and they are on the reactant side. And so the answer is C, like that. So you need to know how to balance a redox reaction in acid and in base. All right, question number 40. It's a very interesting question. Which combination will form a precipitate? I've never even heard of a precipitate. I think I meant to put precipitate. Okay, so which one's going to form a precipitate? Let's go back, and you're like, what's a precipitate, Mr. Dion? Well, let me show you. Get the precipitate right here. Okay, so should be precipitate. There we go. That's a little bit better. All right, let's take a look at these. We got HCl and sodium hydroxide, ammonia, and HCl. What else do we have? We got potassium amide and nitric acid, and then we have potassium hydroxide and cobalt nitrate. You know, I'm going to throw this out there to my students. Does anybody have an idea which one of these would give you a precipitate? Or could anybody tell me what the precipitate would be that would be formed? Anyone? No? Yeah, the answer is D, right? If you take a look at A, what are you going to get from A? You're going to get table salt and water. Well, the last time I cooked pasta, I put some salt in the water, it dissolved. So there's no precipitate there. If I look at the next one, I take HCl and ammonia, I end up with ammonium chloride, which is a soluble salt. If I have potassium amide and nitric acid, I end up with ammonia, NH3, which is water soluble. If you've ever used Windex, you know it's got ammonia, or if you've ever smelled cat pee, okay, there's that methylamine. Anyhow, whatever. No, I think it's ammonia. Yeah, it's ammonia. And then you've got potassium nitrate, which is extremely soluble. So all of these are 100% soluble, right? What do these three reactions all have in common? They're all acid-base reactions. Acid-base. Okay? But then if you combine potassium hydroxide and cobalt-3 nitrate, you end up with potassium nitrate. I'm not going to balance the reaction. And you end up with cobalt-3 hydroxide. Remember that most hydroxides are insoluble. So this is actually going to form a precipitate. It's a solid. Now, a student wrote me an email the other day and asked me an interesting question. The student said, do we have to have the solubility table memorized for the final exam? And what I was thinking is that by the time you've studied an entire year of general chemistry, you kind of get a feel for which compounds are going to be soluble and which aren't, right? If you don't know that potassium nitrate is soluble by this time, that nitrates are soluble, I don't know. Remember that you want to think about what you're doing when you're doing it, you know? So potassium nitrate is an extremely soluble compound, as is ammonium chloride, table salt, and ammonia dissolves in water too. All right, hydroxides like lead hydroxide, cobalt hydroxide, insoluble. All right, let's move on from there. What's the next question about? Something good. Question 45. 45-gram sample of an alloy at 100 degrees Celsius is dropped into 100 grams of water at 25 degrees Celsius. They reach an equilibrium temperature, which is 37 degrees. What's the specific heat of the alloy? To solve this problem, you're going to use Q is equal to MC and delta T, right? This is a good old 1401 problem, General Chemistry 1. Did anybody here or anybody in class right now do an experiment like this in the calorimetry section of the lab? I know that if you took the online lab, you probably didn't, but I know a lot of you took the wet lab, and you would have done an experiment like this, where you would have maybe first measured the heat capacity of a calorimeter or something, and then you measure the heat of neutralization of an acid-base reaction or something. No, nobody did? Okay, anyhow. It's a really classic experiment. In fact, I've done this experiment with nursing chemistry students, which is a lower level than this class. So it's a pretty reasonable experiment. Well, let's take a looky here. All right, so this is question number 41. Question number 41. Well, we have our heat is equal to our mass times our specific heat times our change in temperature. We know that the amount of heat lost by the alloy, right, that metal alloy, when you put it into the water, is going to be equal to the heat gained by the water, and then they reach that final temperature. Remember that the M stands for the mass in grams. C is the specific heat capacity, which is in joules per gram degrees Celsius. Then we have our change in temperature, which I'm sure you know what that is. So let's write down some numbers. We have for our alloy, we have its mass is being 45.0 grams. We're looking for its, just want to make sure I read it. Yeah, we're looking for its specific heat. Okay, so specific heat is what we're looking for, C, for alloy. And then what's our delta T? Well, our delta T is going to be equal to T final minus T initial. What was the final temperature of our alloy? It ended up being 37.0 degrees Celsius, but it started out being super hot, right? Somebody took it out of boiling water. And that's going to be equal to the mass of our water. We have 100 grams of water multiplied by the specific heat of water, which, if you don't have memorized, is 4.184 joules per gram degrees Celsius. Remember that the increment of a degree Celsius in a Kelvin is the same, right? If you have a delta T of 1 degree Celsius, that's going to be equal to a delta T of 1 Kelvin, right? The increment is the same. So even though in the problem they told you that the specific heat of water is 4.184 joules per gram Kelvin, it's the same thing as joules per gram degree Celsius. And you looked at, they're trying to fool you because all the answers are in joules per gram degree Celsius. What's the delta T of our water? It started out at the final temperature was 37.0 degrees Celsius, and the initial temperature was 25.0 degrees Celsius. Now, everybody here can solve for C, right? Rearrange a few numbers. So I've gone ahead and simplified this, and you get, I can't even read my own writing, 2,835 grams times degrees Celsius multiplied by C is equal to 5,200 or 5,020.8 joules. I know I'm carrying too many sig figs. I'm perfectly aware of that. You divide by 2835 grams times degrees Celsius, 2835 grams times degrees Celsius, and you end up with a C that's equal to 1.77 joules per gram degrees Celsius, like that. So there is your specific heat for your alloy, which is B. All right. Take a look at question number 42. It seems like now I'm going to have to rifle back and forth between the exam and my blank document here a little bit. No harm, no foul. Let's go back. Heat technology grand. And let's take a look at this question that deals with enthalpy. Where was it? Somewhere around here. Okay, this is a real classic question, right? I asked you questions like this in the thermochemistry section of General Chemistry 1. It says, what's the change in enthalpy for this reaction? 3 hydrogens plus an ozone produces 3 water molecules. They give you the delta H for this first reaction and the delta H for the second reaction. Now, this one's kind of tough to answer without me rewriting the whole dang thing, but I'll do my best. Since we have 3 hydrogens, right, we have 3 hydrogens over here. The only place that we see hydrogen over here with these 2 reactions at all is right here. So that tells me I've got to take the first reaction and I would have to multiply it by 3. So I'd have to take H1 and multiply it by 3. And when I do that, so I'll say delta H of my reaction is going to be equal to 3 times delta H1. Okay. And then what do I have to do with the second equation? Well, I've got ozone here, right? There's 2 O3 there. The only place that I find ozone, and I only need one of them in the reactant. So what do I have to do? I have to multiply this reaction by a half, but I also have to reverse it. So I'd multiply it by negative a half. So what would that equal? Essentially, you'd be tallying up negative 1/2 multiplied by delta H naught 2, like that. When you do all that spinach, you end up punching all that into your calculator, and you end up with this reaction, okay? And you end up with a delta H for your reaction, which is negative 994 kilojoules per mole, which is D. All right, let's take a look at what's next? Number 43. In which reaction will the entropy of the system increase? So we're looking for an increase in S, in entropy. I'll let you guys take a look at this one and let me know if you think you got an answer. I'd love to hear it. Increase in disorder. Which one is getting crazier? Sorry, let me go back to my chat. I'm having some issues here with my MacBook. Yeah, I see that Joel and Joey both have the correct answer. Right, if you look at A, you got 4 molecules of gas, or 4 moles of gas. We'll say We've got 4 moles of gas over here, and then we end up with 2 moles of gas. So that's a decrease in entropy. If we look at B, we got a solid and a gas, and then we're ending up with only solid in the end. So that's a decrease in disorder. Here you've got 2 components, a liquid and a gas. They're coming together to make one homogeneous aqueous solution. So that's a decrease in entropy. However, in C, you start out with a solid, then you end up with a solid plus a gas. So this one is going to be an increase in S. Or you could say delta S is positive. All right. Number 44. If 345 kilojoules of energy is transferred to a system, so let's highlight that, transferred to a system as heat, while the system does 42 kilojoules of work, what will the change in internal energy of the system be? The change in internal energy of the system after the processes are complete. So we want to figure out the delta U of our system, and delta U is equal to Q plus W. Sometimes instead of delta U, right, delta U is the same thing as change in energy. Okay, it just depends on the textbook. So we've got heat plus work. Well, if the 345 kilojoules, is it positive or negative? Well, the energy is being transferred to the system, right? The system isn't giving off the heat, it's taking in the heat. So this is a positive 345 kilojoules of heat. Then the second part, in terms of the work, our W, it's the system is doing 42 kilojoules of work, right? If the work was being done on the system, it would be positive. However, since the system is releasing or performing the 42 kilojoules of work, it's losing that energy, right? Because it's doing the work. And we end up with 345 plus negative 42. And we end up with our change in internal energy as being 303 kilojoules. That better be an answer. C. All right, number 45 is the only problem that after I put this thing together, I did this problem a couple times, and my wife was like, "What's your problem?" And I said, "Oh, I made a mistake doing this one." So when you do these kinds of problems, this is not a complicated problem. 45 is not a complex problem. We talked about bond dissociation energies enough. However, I think it's easy to goof it up. So make sure you're very judicious when you're counting up the bond. So this is one that I will have to solve on another sheet, but I want you to just maybe have these bond enthalpies listed somewhere. So they're all here. The carbon, hydrogen, carbon, 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 oxygen, single bond, and then the carbon, oxygen, oxygen, hydrogen bond are here, the oxygen, oxygen bond. Anyhow, we need all these bonds. So here's the reaction. You have ethanol plus oxygen gives you carbon dioxide and water. So here's how I solved it. I'll show you my strategy, which might not be the simplest strategy, but I think it's the most foolproof. And you're saying, well, you just made a mistake on this. Well, here's how I would solve this problem. I think this is the easiest way to do it to avoid making mistakes. I would draw out the entire Lewis structure of ethanol. Okay, I have 1 molecule of ethanol. I'm drawing all the bonds out explicitly. I'm reacting with 3 moles of O2. So I'm going to draw 3 molecules of O2. Then what am I forming? I'm forming 2 molecules of CO2. So I would draw out the Lewis structure of 2 molecules of CO2. Let me just get rid of that plus sign so I don't throw anybody off. Okay, like that. And then I end up forming 3 moles of water, 3 molecules, however you want to think about it. So I have 1, 2, 3. There we go. So when we're provided with bond dissociation energies, we know that the change in enthalpy of our reaction is going to be equal to the sum of the bond enthalpies of the reactants subtract the sum of the bond enthalpies of the products. It's the only equation that we look at in chemistry where it's reactants minus products. If you think about it, it makes sense, right? Because you got to put energy in. All the bond enthalpy values are positive values, right? You got to put that positive amount of energy in, and then you subtract the amount of energy that would be released when you form the bonds in the products. So how do you tally all this up? Well, let's start with the carbon-hydrogen bonds. I have 1, 2, 3, 4, 5 carbon-hydrogen bonds in my ethanol. Each one has a value of 413 kilojoules per mole. So I'll put 5 times 413. Done. Then, what else do I have? I have a carbon-carbon single bond. That has a value of 348 kilojoules per mole. What else do I have? I've got an oxygen-hydrogen bond. This one right here. That has a value of 463 kilojoules per mole. What else do I have? I have the carbon-oxygen bond that I left out, which has a value of 358 kilojoules per mole. Okay, still not done, because now I've got the 3 oxygen-oxygen bonds. So that's going to be 3 times 495. So that's all the energy that I have to put in, okay, to break apart all of the bonds in these 4 molecules. Now I'm going to subtract the energy released when I form bonds in my products. I have 1, 2, 3, 4 carbon-oxygen double bonds. So I have 4 times 799 kilojoules per mole. Plus I have 1, 2, 3, 4, 5, 6 oxygen-hydrogen bonds. So 6 times 463 kilojoules per mole. There we go. I tally all that up. I get 4,719 kilojoules per mole. Subtract 5,974 kilojoules per mole. And I get that the change in enthalpy for my reaction is equal to negative 1,255 kilojoules per mole. There you have it. And that is B. Again, I mean, it's just adding and subtracting. But I think the main thing here is that you want to be really careful to tally up your bonds carefully. I remember the reason that I got the question wrong the first time I tried it is because I left out that bond. Okay, I just left out the carbon-oxygen bond. I was like, concern it. All right, where were we? So now we're on to question 46. Question 46. You know what? I think I have room to solve that one over here. And this is a problem that we looked at towards the end of the electrochemistry chapter. I remember I took a good, 20 minutes or so to go over problems like 46. Yeah, again, this is really close to the end of the electrochemistry chapter, which was what, chapter 21? No, chapter 17. Yeah, so this would be chapter 17 if you want to go back and look. This is towards the end of that chapter, chapter 17. It says you got a current of 5 amperes passed through an aqueous solution of chromium-3 nitrate for 30 minutes. How many grams of chromium metal will be deposited on the cathode? The molar mass of chromium is 52 grams per mole, right? You're taking chromium, 3+, you're adding 3 electrons, and you're making solid chromium. That's the whole point here. So the current is causing the chromium-3, and you're making chromium metal. So that means you need 3 electrons to reduce 1 ion of chromium-3. So let's see here. You're doing this for what? 30 minutes, right? And you've got 5 amps. So what I told you is that 5.00 amperes is the same thing as 5.00 coulombs per second. Another thing that we're going to need to solve this problem is the Faraday constant. And the Faraday constant is that it takes 96,485 coulombs, or that is the charge, for 1 mole of electrons. Okay, so with all these things in mind, we should be able to solve the problem. Well, we've got 30 minutes is the amount of time that we pass this current. Now, in 1 minute, I have 60 seconds. And since my current is in coulombs per second, I need my time in seconds. So I've figured out the number of seconds. I have the current, which is 5.00 coulombs per second. That means that seconds cancel out. So I know how many coulombs I've used up over the 30 minutes. Now I know that I have 96,485 coulombs in 1 mole of electrons. But I know that for every 1 mole of chromium metal that I want to deposit, I need 3 moles of electrons, don't I? Right? Those 3 moles of electrons. Again, charge cancels, moles of electrons cancel. Right here, I'd be left over with moles of chromium, but that doesn't answer my question. I need to put in the molar mass of chromium, which is 52.0 grams of chromium in 1 mole of chromium. That cancels. And we end up with the mass of chromium that's deposited as being 1.62 grams. Problem's just dimensional analysis, right? What are the main things that I would think a student might, remember or forget, I forgot to remember to forget, would be how many electrons. You have to know how many electrons it would take to reduce the chromium 3. So you need 3 of electrons. You should know that the Faraday constant, which is given to you in the handout. I'm looking at the handout right here. It tells you the Faraday constant. It tells you it in coulombs per mole and joules per volt times mole. So we have coulombs. So you have to know that an ampere is equal to the number of coulombs per second. You should know that. What else? There was something else that I was. Yeah, I guess that's about it. Faraday constant, current, and yeah, that you need 3 electrons for 1 mole of chromium. If you understand that, you should be able to put the problem together and figure out the mass as being the 1.62 grams.